this solid state line AM, maximum gain AM. What is this 3 dB? Is that we can take the data, maximum data from the signals up to the minus 3 dB compared to the AM minus 3 dB. So it means for a circuit we can get most of the data from here up to this section, which is lower than 3 dB from the AM. So that frequency range at which we are getting this one and we are getting this one is known as bandwidth. Means the formula for the bandwidth is high frequency minus low frequency. This is high frequency, this is low frequency. So in this module, half of the unit we will discuss the calculation of FL and calculation of FH. Generally FL is very small compared to FH, so the bandwidth will be equivalent to, not exactly equal to, FH. Now the figure of merit for the amplifier is that the gain bandwidth product. What is the gain bandwidth product? Gain bandwidth product is the magnitude, means this maximum gain multiplied by the bandwidth, FH minus FM. Formula is here, gain bandwidth product is equal to AM, this one, multiplied by bandwidth. This is the bandwidth. It is generally called gain bandwidth. Means if you are increasing anyone, the second one will be reducing. How we will proceed in this model, in this lecture? So our main concentration will be to calculate the FL and FH. So today I will discuss the FL in detail. From the next lecture onwards, we will discuss the FH. How to calculate the FH. Be remember, this one is the mid-band. Now, in this frequency range, means in the mid-band frequency range, all the capacitances like coupling, bypass and transistor internal capacitance. Where is this capacitance? I am going to show you the series. Circuit diagram is, for example, is this one. See, this one is the C1, C2, CS, coupling capacitor, bypass capacitor, and internal the transistors. From the previous module, analog electronics 1, you know that the transistors have the internal capacitances. So in this lecture and also in the next 2-3 lectures, we will discuss about the coupling capacitors, bypass capacitors and internal capacitor of the transistors. It may be MOSFET or it may be transistor like BJT, like this one. So we will discuss all the capacitances in this module. So going back again here. So in the mid-band range, all the capacitors coupling like C1, bypass, and CS, and the internal capacitance of the transistor has negligible effect and can be ignored in the gain calculation. What meaning is that? Means I will give you the circuit. Then you have to calculate the AM, FL and FH. What is the theory is that when you are calculating the AM, then the capacitors, bypass and coupling and internal can be negligible effect. So this one is the calculation for mid-band. After mid-band, this one is the low frequency range, this is the high frequency range. So to calculate the low frequency range, means at low frequency the coupling and bypass C1, C2 and CS capacitances no longer act as an ideal short circuit and causes the gain to drop. Opposite of this one, at high frequency, transistor internal capacitor causes the gain to drop. It means in this low frequency, in the today's lecture, we have to take care the coupling and bypass capacitances. But at high frequency, we have to take care the internal capacitances of the transistor, BJT or MOSFET. What is the gain function? Means how to calculate the overall gain. I'm going in the circuit again, in this graph again. What it says that the overall gain is the gain of this first section multiplied by gain of the second section, which is AM, into gain of the third section. Means the formula to calculate the overall gain of the amplifier can be expressed as general form. It is general form is AS multiplied by FL multiplied by FH, where FL and FH are the functions that account for the dependence of gain on the frequency in the low range and high frequency range. Means throughout this module we will try to calculate AM, FL and FH. When you are calculating the AM, means mid-band gain determined by analyzing the amplifier equivalent circuit, assuming that coupling C1 C2 and bypass CS capacitors are acting as perfect short circuit, and that the transistors internal capacitances and other stray capacitances for the wiring purpose are perfect open. We can calculate the mid-band gain. Do this one with the help of numerical. So this one is a theory for AM. So come for FL and FH. The transfer function ALS means it is the transfer function at the low frequency. Is AM is mid-band gain multiplied by low frequency in S domain, frequency gain in S domain. By analyzing the equivalent circuit, including the coupling and bypass capacitor, but assuming a transistor internal capacitance are perfect frequency. And opposite of this one, AH equal to AM into FH. You can do this analysis by including the transistor internal capacitances, but assuming the coupling and bypass capacitors are perfect short circuit. So I am going to do the analysis for the low frequency response in today's lecture. Means I am going to calculate this section in detail. This one, determining the low frequency response of the amplifier circuit. As you know that in general the transfer function forms is like this one: S plus omega 1, S plus omega 2. These are giving you the 0, so that's why I write here Z. S plus omega Z1, S plus omega Z2 and so on. And the denominator will give you the poles: S plus omega P1, S plus omega P2, S plus omega P3 and so on. How to calculate the poles and zeros? You know that one. That you have to make this numerator equivalent to 0, calculate the value of S. Make the denominator equivalent to 0, calculate the value of P. So all these conditions are written here. Now, we are usually interested in low frequency response close to the mid band. What is the meaning of this one? It says that we are usually interested in the low frequency response close to the mid band. Means, see, the low frequency range is this one, lower, lower and lowest. But we are not interested to calculate this frequency at that point, frequency at this point, or frequency at this point. We are interested to calculate the maximum frequency in the low frequency. That maximum frequency is at this point. Compared to the other low frequency, highest frequency, we are interested to calculate this frequency, which is just near to the mid band. We are interested in low frequency response, this one, because this one we will discuss in the next lecture. Today I am going to discuss. We are usually interested in the low frequency response close to mid band, so that we can modify the lower minus 3 dB frequency. In many cases, the zeros are at frequencies much lower. In the previous that one, that in most of the cases zeros are at frequency much lower than omega n, and hence there are little importance to determine the omega n. Usually one of the four, for example, see, for zeros frequency is this too large, less impact. For the usually one of the four omega p1 has higher frequency than the other. If in the transfer function or in any circuit, one pole will be the highest, then I will take this process. But if there are more than one or the highest or equivalent, then there is another formula which I will derive after 5 or 10 minutes. Now, for example, one of the pole omega p1 is a much higher frequency than the other pole. Then the frequency is close to mid band will be FL is equal to S divided by S plus pole frequency omega p1, which is this one. Now, which is equation of the first order high pass network. In this case, the low frequency response is dominated by the pole. How to calculate the pole? S plus omega p1 equal to 0, S equal to minus omega p1. And the lower minus 3 dB frequency is approximated equal to omega p1. Means omega L will be equal to omega p1. What is the is that if in any circuit or any transfer function effect and poles have only one pole has much higher effect. So the mid band frequency FL will be equal to S plus omega p. You can calculate the poles. How to calculate? S plus equal to 0, S equal to omega p1 minus omega p1. So you can put in the formula, you can get the omega n equal to omega p1 or FL equal to omega p1 upon 2 pi. What is this omega L? Is this one which we are calculating. So this one is a very easy process when only one pole is much higher than the others. Now, what happens if more than one, means omega p1, omega p2, omega p3 are the highest one or it has dominant, then what happens? We will put the formula like this one. Omega L is equal to poles and zeros. This one is the case when so many poles are there and also zeros are there. At that time we will use this formula. If only one pole, then we will use this formula. So you have to be careful in the numericals that what is the value for poles and zeros. So omega L is equal to omega square p1 plus omega square 2, omega square 3 and so on. Minus, be careful, it is 2. Minus 2 omega 1 square for 0 minus 2 omega square 2 for 0 minus and so on. So by this, using these two formula, we can get the omega L. We can get using this one or we can get using this one omega L. Where is the omega L? It's this one. So we are going to calculate the omega L. And the process to calculate the omega L, this one is omega L, not WL. Don't make the W in the assessment or class test or many exams. It is the omega. Using short circuit time constant to approximate the omega L. What is the process? Process is that when we are calculating the low frequency PN circuit, we are analyzing the low frequency PN circuit, then considering one capacitor at a time while replacing the other capacitor with short circuit. And then calculate the resistor which is looking from this specific capacitor. And then you can use the formula Fl equal to 1 upon 2 pi NL is how many number of capacitors are there, 1 upon C1 RIS. I am going to explain this one. What is Fl? This one we will discuss in the next one. For example, this is the circuit. You know the circuit, you are very familiar with the circuit, you have done so many analysis in the analog electronics. E signal, R signal, C1, RG1, RG2, drain resistance, source resistance, CS, C2, R. It's equivalent low frequency circuit. Left hand side, right hand side, only we have the internal model of the transistor. For this lecture I am going to discuss here. In the assessment, in the test test or main exam or supplementary exam, I will not give you the internal model of system like that. You draw it yourself. To calculate the low frequency, what happens? First see how many capacitances are there. Here, there are 3 capacitances. 1, 2, 3. We are not going to the internal capacitance exist in the MOSFET. So we are looking only the external capacitance. There are 2 capacitances, so we get the 3 omega p. 3 omega p. Then we have to use the formula that which one is if is effective pole or all the poles are effective. According to that, we have to use this one or we have to use this one. In this one, what happens? The simple process I am explaining to you is that first see the input loop. This one. Input loop. In the input loop, suppose that we are sitting on the C1. We are looking from the C1. At that time, sort the other capacitances. Short circuit. This one is short circuit. If this is short circuit, so RS is short circuit. It is not in the effect of this calculation. Now, suppose you are sitting here, means you are looking from this C1. Now look around. What is the resistance looking from C1? Is Rin, what is Rin? The parallel combination of RG1 and RG2. Now you know that how to draw the small signal model. Hold this way, connect to the ground, so RG1 will become parallel to RG. So this is the Rin. The resistance looking from C1 is Rin plus R signal. So the resistance looking from this one is Rin plus R signal from C1. So the omega frequency due to frequency is pole or 0. How you will calculate? For that purpose, what you can do, I am telling you here, I think it is not in the lecture note. Take only this small section, V signal, R signal, C1, put here any voltage, for example V1, then this one, and look up. For this section, calculate the ratio of this V1 divided by V signal, and then make the transfer function for this small section. Make the transfer function. Then find the poles and zeros. When you calculate the poles and zeros, then maybe you will get the formula something like this one. Then you can decide that it is the pole dominant or zero dominant. So after calculating the poles and zeros, in this section for this example, you will find that the pole is more effective, more dominant. So the omega P1 you can calculate omega for this section P1 like this one is equal to 1 upon C1 R signal plus Rin. Come back again on the circuit. So this one you have calculated the C1. Same process you have to follow for the second means right hand side section. Suppose you are sitting on the C2, we are looking for the resistance from this C2, it is RL plus RD. Be careful in the class test, assessment or in the main exam, I will give you some question which is parallel combination. Not every time the series combination. Here in this question, the resistor looking from C2 is R1 plus RD. Sorry, RL plus RD in this loop. So the omega, you can also find the transfer function. Taking this voltage, assuming voltage here, you can find the transfer function poles and zeros. Then you will get that this is the pole dominant also. So you will get the omega P3 is equal to 1 upon C2 RD plus RL. So you till now you calculated the omega 1 and omega 2. Now for the center X, calculate the omega. What happens in this section? To find the poles and zeros, you can put the voltage input, voltage output, find the poles and zeros. You can one more thing. What happens? This here, it introduces a low frequency pole and a lower frequency. The resistance ROS, this resistance between from this section, pushing back into the transistor. Poles now. We have separated already only this one. And to see that how it works. Looking from the CS. What happens if I am looking back into the effect? Here is one resistor, 1 upon GM. So the resistance for the purpose of pole looking from CS will be RS and 1 upon GM. This 1 upon GM is not in the series. This will be parallel. You can think that like imaginary resistor 1 upon GM. 1 upon GM was this terminal connected to grounding. 1 upon GM and RS is parallel like this one. So that is the resistor multiplied by CS. You will get the omega P. Now, what happens? You get omega P1, omega P2, omega P2, omega P3, and also you get the omega. You can use the formula to find the transfer current. I am showing you one more example, then we will go for the final formula. Now, this one is the same question, but here it is the BJT, bipolar junction transistor. I will show you this circuit. You have to design your own this type of circuit. It's equivalent circuit. What happens here? Again, we are going to find the poles. Then we will try to find the frequency for the low frequency side. Now this is the circuit. First, on the left hand side, what is the condition? If you are looking from C1, short circuit, other capacitors. Short circuit. So if it's short circuit, no need of RE. So it means this R pi is connected to ground. Now, suppose you are sitting here on C1, you are looking the capacitance from, we are looking the resistance from C1. Start from here. R1 and R2, you know, connect this one to the ground, so it will become parallel to each other. That's why resistor looking from C1 is RB. So this R pi will become parallel to R. So the resistance looking from C1 is equal to R square plus parallel combination of RB and R pi. Like this one. Here RC1 is equal to R signal plus RB parallel. Why I am calculating resistance? Because we already have the C1 in the circuit. So we can put the frequency like this one, FL equal to 1 upon 2 pi into RC1. This is RC1. You can put all, you can put only the RC. short circuit the other capacitances. What's your thinking? Is this RL plus RC equal, or any other effect of this resistances will come? Yes, it is correct. There is no any effect of the previous resistance because you make it short circuit. You make it short circuit, so it is connected to ground. So this all are connected to ground. And this one is the GM into VBE. You know what is GM into VBE. So the resistance looking from C2 is RL plus RC. So the formula for this one is RL plus RC. Now, the main section of this numerical is the center one. What happens in the center one? We have to see the resistor looking from CD. Short circuit this one, short circuit this one. If you are looking from here is RC. Now you have to decide this R pi parallel or series to R pi. Because this R pi is here, is in the circuit, not like a previous one like 1 upon GM, but here R pi this R pi is not other sections, R signal and RB. So we have to be careful about this section. Do the analysis in detail. I am going to show you how it becomes. I am going to calculate the resistance looking from here is RE will become parallel to this RE. All these are connected. See this R signal. In series with RV parallel R signal. For that purpose, again, see what the confusion was there. Everything is correct. You did all the calculation correct. Means the RE parallel R pi plus RB parallel R signal. What was the mistake we did? Is see here at this point. First we have to match this current IC. Now this resistance is coming with the I. This resistance is coming with I. So first we have to make equivalency for the base current and emitter current. For that purpose, in the BJT, IC plus IB is equal to IC. Now IC is equal to beta IB. In case of IC, beta IB. Take the formula IB. Beta plus R. Multiplication factor beta plus 1. So that's why this beta plus 1 comes give you I. So that's the reason the beta plus. After getting all these three resistances, you have the three capacitances. So the frequency equation 1 upon 2 pi. And then you can go and read this one. What happens in this is that the equation 7 in this one, it can follow where R dash E is usually the smallest resistance. The total capacitance is minimized by selecting the CE to make the 1 upon CE RE term dominant term. For example, say 80%. So what happens in this one? The center section means in this main section has the effect of 80% of the frequency, and the remaining two sections you can say approximately 10% and 10%. So you have to calculate the center section very carefully. I am going to show you one numerical. How to solve this numerical? After looking my lecture, don't see the solution first. You have to try to do it yourself. Take the plain paper, start solving this one, and after solving, then you can match this numerical with the solution. What is the question? Theta is given to you 100, Vt 25, ICQ, question correct. For a collector is 1 milliampere, and ignore the R0. Determine the low frequency minus 3. Low frequency often for this amplifier circuit using the method of SC-DC. So you can calculate this. How to calculate? First you have to draw the small signal model. This one, the small signal model is like this one. So you have to calculate the resistance looking from C1, resistance looking from C2, and the resistance looking from C3 using that formula which we derived just now with the beta plus 1, help of beta plus 1. To calculate the resistance looking from C1 is RB parallel, sorry, this is the, we are looking from the RC is equal to RB in series with RC. Why? Because here what happens? We have to take the parallel combination RB parallel R5 like in the formula. RB parallel R5. So we use that formula. Resistance looking from C1, you can name it RC1. R signal is given to you 50 plus R1 parallel R2, then calculate this. Parallel R5 is not given. Beta 100 volt divide by 1 you get the 2.5 kilo. So you can calculate the value of resistance looking from C1. Same process you can follow for the capacitor 2 to calculate the resistor looking from C2, and then you have to using the formula calculate the resistance looking from CE. After calculating all those three those three resistances looking from capacitor like RC1, RC2 and R-E. After calculating, you can calculate the 1 upon R1C1, 1 upon RECE, 1 upon R2C2. Put the values, find the values here. Then you can calculate the omega L is equal to, using this formula, put all the values. Or you can calculate the FL. So this FL is the main analysis for the today's lecture. Where is the FL in the circuit? Means in the graph is here, FL. So today's lecture is devoted to calculate the FL here. Why I am calculating this FL? Because there are so many values lower than FL, but we are interested to that value, that low frequency response which is close to the midband. This is the midband. So we are interested to calculate the FL. So using this process we can calculate the FL is here, FL. So out of these there are three values of omega L. You can see that the center one, means due to the emitter section, is the highest one, which is approximately 80% of others. It is not 10 and 10%, but approximately Why I am saying approximately? Because in your design project, if you want to design an amplifier, so you have to select the components carefully such that the center one will be give you the 80% of the frequency range or gain. Then in the next lecture, I will start the high frequency response. Thank you.